Hello and welcome to my kitchen. So this is going to be the first of a series of videos. The goal here is that each day in the first video I'm going to try and introduce the concept from a theoretical standpoint, and then in the second video we'll go to pen and paper and I'll be narrating some problem solving as well as some solutions to some problems as we go through. So the last time I saw y'all, last Friday, we were doing a derivation in which we had two masses on the end of what we said a massless meter stick, and we were twirling it. And we figured out that there was this weird term when we were looking at the kinetic energy, because what we did is we looked at the kinetic energy of the system as being the sum of the kinetic energies of all the individual particles. And we found out two things. One, that we could derive this weird expression that looked a lot like our 1/2 mv squared equation, but it was 1/2 this weird term and then omega squared. And we found out that that weird term that we didn't know much about was based on not only about the masses, but where the masses were. And at the end of class, I called that the moment of inertia. And that's actually what we're talking about here today, is the concept of moment of inertia. Now, what we said about moment of inertia is it's essentially something we will call rotational inertia, right? In the same way that mass is normal inertia, and mass is the tendency of an object to persist in its straight line motion. Now we're going to be a little bit more precise about that. It's the tendency of the center of mass to persist in its state of motion, or a moderation of the effect of net forces about how difficult it is to change the straight line motion of an object. We're going to have this moment of inertia term that's going to be the same concept but for rotation. So it's whatever this term is, which we're going to call I, is going to be about the tendency of objects to persist in their state of rotational motion, or a measure of how difficult it is to change the rotational state of an object. So those words and phrases are very particular. So I hope you're taking some notes about that. Now, what I wanted to talk about today was this notion that we found when we did this derivation, that we did that rotation about two separate axes. The first axis was through the center of mass of the system, right in the center of that meter stick. And the second one was 0.2 meters off of that. And we found out that that term was different based on what the rotational axis is. Well, what we actually found out, by the way, was that the kinetic energy was different based on what that axis was. But we're going to see that those two things are synonymous. So what I want to talk about today is this concept of moment of inertia. So regular inertia, all that matters is how much mass do you have. That determines the degree to which that thing moderates motion. With moment of inertia, what also matters is not actually how much mass, but how that mass is distributed about the axis of rotation, right? And that's going to be the key idea. So in order to help you figure this out a bit, what I want everyone to do is just stop this video for a second and go find, I don't know, a broom. So stop the video. All right, so now you are back. And so hopefully with a broom or a mop or some sort of stick, what I want you to do is grab the stick or the broom or the mop at where you think the center of mass is. So how can we figure that out? Well, we already talked about the center of mass as the balance point, right? So the center of mass of this object is somewhere between my fingers. And what I want you to do is carefully and look around, like I have a light fixture here, I'm going to be careful, I have a table here, and I'm going to rotate this mass about the center of mass and get a sense of that. Now, then what I want you to do is grab the end and rotate that same mass about that same point, right? Hopefully what you'll find or feel is that this is a lot more difficult than this. In fact, the more you move out from the center of mass, the more difficult it is to cause the same rotation. That's the moment of inertia concept, okay? Now there's another concept involved there that we'll get into in a later video, but just it's more difficult to rotate things not through its center of mass. And so that axis matters. Another way we can rotate this is by rotating it down the long end. You'll find that this is very simple to rotate. It's actually a lot easier than even rotating about this. Well, why? Well, the concept of moment of inertia says that it depends on how the mass is distributed about the axis of rotation. So if we look at this, most of the mass is pretty close to the axis of rotation, so that makes this easy to rotate. Versus this, there's a lot of mass that's far from the axis of rotation, so it's not as easy to rotate. Versus this, where most of the mass is quite far, oops, there goes my lamp, from the axis of rotation, making it more difficult to rotate. Some more examples of that. Our textbook. I can rotate my textbook across a bunch of axes. I could rotate it like this, I could rotate it like this, and I can rotate it like this. Based on what we talked about, which of those is going to be the one that has the greatest resistance, not resistance, let's not use that word, that will moderate the effect of the change more, i.e. harder to rotate. So would it be this one, or this? Well, hopefully you said this, because in this one, most of the mass is actually quite far from the axis of rotation comparatively. This axis, look at this length, most of the mass is not all that far from the axis of rotation versus this one, where more mass would be further from the axis of rotation, and this, we'd have more mass far from the axis of rotation. So the shape of the object matters, but also so does the axis. Because I could rotate like this, not that bad, but if I try and do the same thing about the end, that's a lot harder. So what we're gonna learn over the next 2 days is the following: how to calculate the moment of inertia. Now, what we're gonna do is we're gonna start by just looking at point masses in the same way we did for center of mass, because there's a good analogy there we'll find out. So for point masses, a collection of point masses, we're going to find moments of inertia, and then we'll look at things like sticks, flat planes, discs, hoops of different types. I know the most valuable substance on Earth, right? And so that's what we're going to do on Tuesday, is moment of inertia for continuous masses. And if you haven't guessed already, that's going to require calculus. So in the next video that I'm going to post, I'm going to be walking you through some stuff pen and paper. And then tomorrow's video is going to talk about moments of inertia of continuous masses, and it's going to largely be another pen and paper derivation-based thing. And then Wednesday, we're going to talk about torque. We'll be back to some demonstrations. I'm also going to attach a couple of extra videos from YouTube for you to look at, because there's some interesting concepts about center of mass and rotation that I'll go through in some later videos. Okay, thanks.